The saliva goes first, not the blood, not the eyes, not the skin splitting open the way every movie told you it would. The saliva, the thin film of moisture on your tongue, the wet surface of your lips, the liquid lining the back of your throat that goes first, and it goes in a way you can feel. Not pain, something stranger than pain, a fizzing, a lightness on the tongue that your brain cannot immediately classify because nothing in your entire evolutionary history prepared it to classify this. You are not burning. You are not freezing. Your saliva is boiling at body temperature because the pressure holding it in liquid form has just disappeared. And the last thing your conscious mind will register before the darkness comes is that specific sensation, that impossible fizzing on the surface of your own tongue. We know this because one man felt it and lived to say so. His name was Jim LeBlanc. He was not an astronaut. He was a technician, the kind of person whose job title appears in the credits of a mission nobody remembers. The kind of person whose work is only discussed when something goes wrong. On December 14, 1966, he was inside Chamber B of the Space Environment Simulation Laboratory in Building 32 at the Manned Spacecraft Center in Houston, Texas. He was wearing a prototype moon suit. He was testing its pressure integrity. The hose that supplied pressurized air to his suit became disconnected, not dramatically, not with a bang, but in the way that things fail in test environments, quietly and without warning, and his suit pressure dropped from 3.8 pounds per square inch to 0.1 in 10 seconds. 10 seconds. He stumbled backward. He felt the fizzing on his tongue. And then he was gone, not dead, but unconscious, his body already beginning the cascade of failures that the engineers watching through the chamber glass had no specific protocol for. Because nobody had agreed yet on what the protocol should be. The chamber would normally take 30 minutes to repressurize. They blasted it back to atmospheric pressure in 87 seconds. LeBlanc regained consciousness as the chamber monitors called out 14,000 feet equivalent. He survived with a sore ear. He later became a division chief. He went home that December evening, presumably for dinner, and the universe did not give him a certificate or a headline or a medal for having been, briefly, the closest thing to a human being in deep space that had ever existed on Earth. What he gave back in exchange for his 87 seconds was the most precise first-person account we have of what the body reports at the edge of vacuum. And what it reports is not what anyone expected. This is where the story starts to go sideways from every version you have heard before. The version most people carry is cinematic, and the cinema got it from somewhere real, from a reasonable extrapolation of physics that turns out to be wrong in almost every specific detail. In the movies, the body explodes, or it freezes instantly, skin going blue-white in seconds, ice crystals forming on eyelashes, or the eyes bulge out of the skull, or the blood boils in some visible, dramatic, rupturing way. These images are vivid. They are also wrong, not approximately wrong. Not wrong in the way that a simplified model is technically incomplete, wrong the way a story is wrong when the person telling it has never been in the room. What actually happens is stranger, and the strangeness lives not in the individual events but in the order, the sequence, the hierarchy of what the body surrenders first. Start at the beginning. Start at the moment the pressure goes. Your lungs know before anything else, because your lungs are the one organ in direct communication with the outside environment. The instant the pressure differential inverts, the instant the outside pressure drops below the inside pressure, the air in your lungs wants out. Not slowly. The pressure differential is catastrophic by any standard your body has ever encountered, roughly equivalent to having spent your entire life at sea level and having the atmosphere yanked away in a single moment. The air expands. It seeks the exit. If you hold your breath, if the ancient animal self-protective instinct fires and you clamp your throat shut, the expanding air has nowhere to go, and it will rupture the alveoli, tear the delicate tissue of the lung wall, cause the kind of barotrauma that fills the thoracic cavity with blood. The correct response, the counterintuitive response, the response that requires you to override every instinct you have in the moment your environment turns lethal, is to let the air go. Open your mouth. Open your throat. Let it out. The lung empties in the first second or two, and the lung survives empty. Damaged, compressed, dysfunctional but structurally intact. Most people, faced with sudden exposure to vacuum, would hold their breath. Most people would die faster for it. Simultaneously, at the moisture surfaces the eyes, the mouth, the throat, the wet tissue of the airways, ebullism begins. This is the word that belongs to this phenomenon, and it belongs to a man named Julian Ward, who was 35 years old when he coined it and died 6 years later without seeing it enter common use. Ebullism, from the Latin ebulire, to bubble up, to boil out. Ward was a captain in the United States Air Force Medical Corps, a flight surgeon at the School of Aerospace Medicine, and in October of 1956 he published a paper in the Journal of Aviation Medicine called The True Nature of the Boiling of Body Fluids in Space. And in that paper he named the thing that happens at the Armstrong line and explained, with a precision that the field had not previously managed, why it is not the same as the boiling you produce by adding heat. Boiling in the ordinary sense is a thermal event. You add energy, the temperature rises. At 100 degrees Celsius at sea level, the thermal energy of water molecules exceeds the pressure holding them in liquid form, and they escape as gas. Ward's contribution was to explain that what happens to body fluids above 63,000 feet above Armstrong's line, the altitude above which atmospheric pressure drops below the vapor pressure of water at normal body temperature, is pressure-driven, not heat-driven. The temperature does not change. The pressure does. And when the ambient pressure falls below 47 millimeters of mercury, the boiling point of water at normal body temperature drops to exactly 37 degrees Celsius, which is to say, to the temperature you already are. Your body fluid is already at its boiling point. You just needed the pressure to go away. Harry Armstrong discovered the line that bears his name in the 1930s while working at Wright Field in Ohio, running experiments in altitude chambers, pushing animals and eventually carefully calibrated human tests toward the edge of what the atmosphere would permit. He was trying to understand where the hard ceiling was. Not the ceiling of consciousness, not the ceiling of oxygen deprivation, those were well mapped by then, but the ceiling where the body itself became the hazard, where the physics of fluid pressure made survival a matter of seconds regardless of oxygen supply. He found it at roughly 63,000 feet. He called it the limit. He did not yet have Ward's word for what happened there. He just knew that above that altitude the body began to do something the body was not designed to do, and that the something was irreversible past a certain point. Ward gave the something its name. And then Ward died in a plane crash near Hahn Air Base in Germany, and the name entered the literature, and the man who gave it essentially disappeared from the story. The Aerospace Medical Association named an annual award for him. Most people who have read extensively about vacuum exposure have never encountered his name. Back to the sequence. Back to the first second. The saliva goes first because saliva is a moisture surface in direct contact with the pressure drop. Your tongue is not protected. The thin film of water on the mucosal surface of your mouth has no structural barrier between it and the vacuum. At 47 millimeters of mercury, which is effectively what you have in deep space, which is effectively zero atmospheric pressure, relative to any number your biology recognizes that moisture flashes to vapor. Not painfully, not with the heat of a burn. It simply transitions state, and as it does it creates the sensation Jim LeBlanc described, something between a fizzing and a lightness, something the conscious mind has no accurate category for, something that arrives and then departs as consciousness departs, the last data point before the system goes dark. The eyes follow. The moist surface of the cornea begins to vaporize. There is no pain here. The cornea has limited pain receptors in this context, but the eye begins to lose the moisture layer that keeps it functional, and the corneal surface can freeze in the temperature differential at the eye's surface. Not freeze the way Hollywood renders it, with the whole eye turning white and crystalline. Freeze locally, at the surface, the moisture layer on the cornea undergoing the same pressure-driven phase transition as the saliva, taking heat with it as it vaporizes and leaving the surface temperature briefly below freezing. This is recoverable. The cornea, with repressurization and rehydration, can return to function. We know this because Kittinger's hand told us something close to it. Joe Kittinger, August 16, 1960. Project Excelsior, a United States Air Force program to test high-altitude parachute systems by jumping from a helium balloon at the edge of the stratosphere. On the third and final jump, ascending to 102,800 feet in an open gondola, Kittinger's right glove failed to pressurize. The seal at the wrist gave way, and his right hand was exposed to conditions approaching the Armstrong line, not full vacuum, but near enough that ebullition began. His hand swelled to roughly twice its normal size. He described it as painful and then as useless, the nerve signals becoming unreliable as the tissue distorted, the hand becoming a thing at the end of his arm that no longer responded accurately. He continued the ascent anyway. He jumped anyway. He fell for 4 minutes and 36 seconds, the longest free fall in history at that point. The atmosphere thickening around him as he descended, and his hand repressurized as the pressure climbed back through the Armstrong line and then through the altitudes where a human can function, and by the time he landed the swelling had begun to reverse. 3 hours later, full function had returned. This is the detail that every account of Kittinger's jump mentions and then moves past too quickly. Full function returned. A human hand that had been, for the duration of a record-breaking stratospheric jump, an object undergoing near vacuum ebullition, came back. Not perfectly, not without damage that may have been subclinical and never fully measured, but functionally. The body holds. The skin does not rupture. The tissue swells but does not burst. This is one of the most counterintuitive findings in the entire history of this research, and it arrives from a man who made the decision to continue ascending with a failing glove because the mission mattered more to him than the hand. Here is what the skin is doing, and why it does not burst. Your skin is an organ. This is a thing people know intellectually and do not feel at the level where it matters. It is not a passive wrapper. It is a structural element with tensile strength, elasticity, and a capacity to withstand pressure differentials that most people have never had occasion to think about. The vapor pressure of water at body temperature is 47 millimeters of mercury. Atmospheric pressure at sea level is 760 millimeters of mercury. The delta, the difference your skin would need to contain to prevent the body from swelling visibly, is enormous. And yet the skin can contain it, at least partially, at least for long enough. Research on animals exposed to vacuum research that dates back to the 1960s and extends through decades of aerospace medicine study shows that the body does swell in vacuum. Consistently, measurably, the soft tissue expands. In some animal studies, the total body volume roughly doubled, but the skin held. The subcutaneous tissue swelled against the dermal boundary, and the skin stretched, and the skin did not tear. What this means in practice, you would not look like yourself after 30 seconds of full vacuum exposure. You would look like something drawn by someone who had been told about a human body but had never seen one. But you would be structurally intact. The visible catastrophe, the rupture, the spray, the Hollywood ending, does not happen. The invisible catastrophe is what kills you, and it is happening in places you cannot see. In the veins. This is where ebullition becomes lethal in a way that the body cannot hold together against. The venous system operates at lower pressure than the arterial system. The large central veins, the ones close to the heart, operate at pressures that are already close to the vapor pressure threshold under normal conditions. When the ambient pressure drops to vacuum, these veins are the first vascular structures to experience bubble formation. Vapor bubbles forming in venous blood create something the cardiac literature calls vapor lock, and the term is accurate in its mechanical bluntness. The bubbles block flow the way an air pocket blocks a pump. The heart is still beating. The heart will keep beating, remarkably. For minutes after vacuum exposure, the myocardium is one of the most durable structures in the body and it keeps contracting even as the system it is supposed to be pumping through is collapsing. But if the venous return to the heart is blocked by vapor bubbles, the cardiac output drops, the arterial pressure falls, and the brain begins to receive insufficient oxygenated blood. This is the mechanism of loss of consciousness in vacuum exposure. Not explosion, not freezing, not suffocation in any simple sense. It is the brain going dark because the cardiovascular plumbing has vapor locked, because the physical chemistry of pressure and phase transition has turned the blood itself into foam. 12 to 15 seconds. That is the window from pressure loss to loss of consciousness at full vacuum equivalence. 12 to 15 seconds of useful function, though useful is doing significant work in that sentence, because the system is already compromised, already non-functional in ways that would prevent meaningful action. The aerospace medicine literature uses the phrase time of useful consciousness, and it is a specific technical term with a specific technical meaning. The period during which a person experiencing acute oxygen deprivation and pressure loss retains the cognitive capacity to take corrective action. At full vacuum, that time is measured in the low tens of seconds. At explosive decompression, not gradual, not slow, but instantaneous pressure loss, the effective time of useful consciousness may be half of that, 6 to 8 seconds. Your body is still standing. Your heart is still beating. You are looking at your hands, and your hands look wrong, slightly swollen, the skin tight, and then you are not looking at anything. Jim LeBlanc's last conscious memory was the fizzing on his tongue. He did not remember the stumbling. He did not remember hitting the floor of the chamber. He did not remember the 87 seconds. He came back into consciousness as the chamber pressure climbed through the equivalent of 14,000 feet, and the first sensation he reported was not pain, but a kind of general confusion about where he was in time. The chamber staff were looking at him through the glass. The repressurization pump was still running. R.L. Clay, a technician whose name does not appear in most accounts of this incident, whose name was retrieved decades later by an engineer named Hank Rotter, who was in the room and wanted the record corrected. R.L. Clay had been the one to reverse the pump immediately when the backpack malfunctioned, had acted faster than the protocol required, had made the decision that saved LeBlanc's life not through training or heroism, but through what Rotter later described simply as presence of mind. Clay's quick action bought the 87 seconds that allowed LeBlanc to go home that evening, instead of becoming a very different kind of data point in the aerospace medicine literature. The body, during those 87 seconds, was continuing its cascade. Not stopping. Not waiting. The cardiovascular system was operating in a compromised state, the heart beating against a vapor-locked venous return, the arterial pressure dropping, the chambers of the heart cycling with reduced efficiency as the load it was designed to handle became something it was not designed to handle. The lungs, emptied by the pressure differential, were not exchanging gas. There was no gas to exchange. The tissue was swelling subcutaneously, not to twice its volume. LeBlanc's exposure was too brief for the full animal study picture to manifest, but measurably, the soft tissue responding to the pressure drop with the only response it had available, expansion. The corneal surfaces were in some degree of distress. The sore ear, LeBlanc reported, was experiencing barotrauma, as the delicate pressure-sensitive structures of the middle ear responded to the differential. And then the pressure came back, and all of it started to reverse. This is the other thing the movies never show, and it is in some ways the most remarkable part of the story. Recompression works. Not perfectly, not without residual damage that depends on duration and degree of exposure, but in the short window cases, the cases where the repressurization happens, within the first 90 seconds the body reverses. The vapor bubbles reabsorb. The venous circulation restores. The cardiac output climbs. The brain, which has been running on the oxygen already dissolved in its tissue, the brief reserve that evolution built in for exactly the kind of emergency that evolution never anticipated but apparently hedged against anyway, receives oxygenated blood again and wakes up. The saliva returns to liquid. The corneal surfaces rehydrate. The swelling subsides. You come back. Not everyone comes back. The window is narrow, and the variables are unforgiving. But the window exists, and its existence changes something fundamental about how we understand this subject. Deep space is not instantly lethal. The human body in deep space, unprotected, is not a bomb going off. It is a system under catastrophic stress, failing in a specific order, fighting the failure in the specific ways that a system built for a different environment can fight the wrong kind of failure, and for a period measured in tens of seconds, it is still there, still running, still technically a person. That window is everything. The whole architecture of human spaceflight, the suit design, the airlock protocols, the emergency repressurization procedures, the personal rescue sphere that looks like a large fabric ball and is the last refuge when everything else has failed, all of it is built around that window. Extend the window. Protect the window. Make sure the window is never the thing that fails. Harry Armstrong found the line in the 1930s and did not have the vocabulary to name what happened when you crossed it. Julian Ward named it in 1956 and died before he saw the naming matter. Jim LeBlanc crossed it in December of 1966 in a chamber in Houston and came back with a sore ear and a memory of fizzing. The window exists because of all of them. The window exists because of R.L. Clay, who reversed a pump faster than the protocol required, whose name almost did not survive the telling of the story. Now pull back, because the script has been inside the body and inside the chamber, and there is a larger geography to account for. Deep space, in the title of this thing, is doing specific work. It is not low Earth orbit. It is not the altitude where the International Space Station maintains its carefully pressurized atmosphere at 14.7 pounds per square inch, where the worst-case scenario involves a hull breach small enough to patch, where emergency re-entry is theoretically possible within hours. Deep space is the place beyond all of that, beyond the Van Allen radiation belts, which wrap the Earth in a magnetic shield that deflects the constant stream of charged particles from the Sun and from the galaxy beyond. Beyond the heliosphere, where the solar wind that pushes outward from the Sun finally fails against the pressure of the interstellar medium, and the Sun's influence ends at the heliopause. Deep space is the place where the body is no longer shielded by anything the Earth has to offer, and where the vacuum exposure problem acquires companions. Consider what changes when you move the thought experiment from Building 32 in Houston to interstellar space. The vacuum is the same vacuum. Pressure is zero regardless of whether you are 10 miles above Houston or 10 light-years from any star. The boiling point of your saliva does not care how far you are from civilization. The arterial vapor lock does not require a specific address. The 12 to 15-second window to unconsciousness does not extend or contract based on the distance to the nearest inhabited planet. In those fundamental mechanics, deep space and the vacuum of the chamber in Building 32 are identical. The body follows the same sequence in both places, but the context around that sequence changes in ways that matter to the story. Radiation is the first change. In low Earth orbit, the Earth's magnetic field provides partial shielding against galactic cosmic rays, the high-energy particles that stream constantly through the galaxy from supernova remnants and other extreme astrophysical events. The Apollo astronauts, transiting the Van Allen belts on their way to the Moon and back, reported seeing light flashes with their eyes closed, the visual cortex responding to cosmic ray particles passing directly through the skull. This is not metaphor. This is physics. A charged particle moving at a significant fraction of the speed of light, passing through brain tissue, ionizes the atoms along its path and triggers neural firing that the brain interprets as light. The astronauts saw lights that were not there because their brains were being threaded by particles from supernovae that exploded before the Earth formed. In deep space, beyond the heliosphere, the flux of galactic cosmic rays is substantially higher than anywhere in the inner solar system. The solar wind provides a modest barrier. The heliosphere is a bubble of solar particle pressure that partially deflects or modulates the incoming galactic radiation. Step outside that bubble, as the Voyager probes did. Voyager 1 crossing the heliopause in 2012, Voyager 2 following in 2018, and the cosmic ray flux increases measurably. An unprotected human body in interstellar space would be absorbing radiation at a rate that matters on the scale of minutes, not years. The DNA damage, the cellular disruption, the increased probability of radiation-induced cancer, these are not acute hazards in the 1-second window the title is examining, but they are the second layer of what deep space does to the body. The layer that operates on a longer timeline than the vacuum mechanics but is no less real. The second change is temperature, and this is where the popular mythology is wrong in the opposite direction from the explosion myth. Space is often described as cold incomprehensibly, instantly cold, and the description is true in the cosmic average and misleading in the specific. The cosmic microwave background radiation puts the temperature of deep space at about 2.7 Kelvin, minus 270 degrees Celsius, a temperature so close to absolute zero that it is almost a definition of cold rather than a measurement of it. But temperature is a measure of energy per particle, and in vacuum there are almost no particles to carry energy to or from your body. The mechanism of heat transfer in space is not conduction, there is nothing to conduct through, and not convection, which requires a fluid medium. The only mechanism is radiation. Your body radiates heat constantly, as all warm objects do, as electromagnetic radiation in the infrared spectrum. In vacuum, that radiation is the only way heat leaves you, and it is slow. The calculation that follows from this is the one that surprises people most consistently. In the first second, in the specific second the title is examining, your body temperature changes almost not at all from radiation loss. The surface of your skin might begin to drop as the evaporative cooling from the boiling moisture surfaces takes heat away. The latent heat of vaporization of water is substantial, and the saliva and corneal moisture and airway moisture flashing to vapor are each taking thermal energy with them as they go. This is a real cooling effect, and it is not trivial. But it is local. It is a surface effect. The core temperature of your body, in the first second, has not changed. You are not freezing. You will not be frozen for a very long time. Estimates for how long it would take an unprotected human body in deep space to freeze through radiative loss alone run to 18 to 36 hours, depending on the assumptions. You will have been dead for many hours before your body is cold. This is the part nobody wants to hear. The clean ending, the quick mercy of instant cold, is a myth. The actual experience, to the extent that we can reason from the physiology and from the handful of real cases, is not clean. It is the sequence. The fizzing saliva, the failing circulation, the darkness at 12 to 15 seconds. And then, if no one reverses the pump, the body continuing its cascade in the dark, the heart beating for minutes against a compromised system, the temperature dropping slowly through radiative loss, the vacuum continuing to do its work on a system that is no longer conscious of it. The 3 men who died in space, the only 3 people whose deaths occurred above the Kármán line, the only 3 human beings who left Earth's effective atmosphere and did not come back alive, did not die from explosion or instant freezing. Georgy Dobrovolsky, Vladislav Volkov, Viktor Patsayev. Soyuz 11, June 29th, 1971, 168 kilometers above the surface of the Earth. They had spent 23 days aboard the Salyut 1 space station, a record at the time, the first successful long-duration mission to a space station, a genuine triumph of the Soviet space program. They loaded their scientific specimens into the descent module. They undocked. They retrofired for re-entry. During the separation of the orbital module and the service module, the explosive bolts that were designed to fire sequentially fired simultaneously, and the shock unseated a seal on a pressure equalization valve located beneath the cosmonauts' seats, and the valve opened, and the atmosphere of the Soyuz began to vent to space at 168 kilometers altitude. They were not wearing pressure suits. The redesign of the Soyuz that had preceded their mission had removed the suits to allow a 3-person crew in the tighter vehicle. Without the suits, There was nothing between the cosmonauts and the venting atmosphere except the capsule walls and a valve they could not reach in time. Patsayev's body was found positioned near the valve. He may have been trying to close it. Alexei Leonov, who had been the original commander of the mission before a crew substitution 6 days before launch, Leonov, who had trained with the same spacecraft, who knew its systems, later said that he had warned the crew before flight to manually close the valves between the orbital and descent modules, that he did not trust them to close automatically. He had developed this procedure himself during simulator time, an intuition, a trained unease with that specific valve in that specific configuration. The crew apparently did not follow his advice. After the mission, Leonov went back to the simulator and tried to close one of those valves himself. It took him nearly a minute. The cabin atmosphere was gone in 40 seconds. The biomedical sensor on Dobrovolsky's body, the only one of the 3 who was instrumented, recorded cardiac arrest 40 seconds after the valve opened. The autopsy at Burdenko Military Clinical Hospital in Moscow found hemorrhaging in the blood vessels of the brain, bleeding under the skin, bleeding in the inner ears and nasal cavities. The blood contained heavy concentrations of lactic acid, the chemical signature of a system that had stopped receiving oxygen and was burning through its emergency reserves. The oxygen and nitrogen in their bloodstreams had formed bubbles that ruptured vessels. They had been conscious for something approaching 20 seconds after the pressure began to drop, and then they were not. The capsule landed on schedule, 90 kilometers southwest of Karazal in Kazakhstan. The recovery team knocked on the side of the capsule. There was no response. When they opened the hatch, they found 3 men seated in their couches, dark blue patches on their faces, trails of dried blood from their noses and ears. Dobrovolsky was still warm. The doctors attempted CPR. It was too late by at least 15 minutes, probably more. The Soviet state media did not announce the cause of death for almost 2 years. They emphasized the accomplishments of the mission. NASA, preparing the Skylab program, was deeply alarmed they had no information about what had actually killed the cosmonauts, could not rule out that prolonged weightlessness had proved fatal in some way they had not anticipated, and spent a significant period of uncertainty developing contingencies for a cause of death that turned out to be entirely mechanical. A valve. A set of explosive bolts that fired together instead of sequentially. 40 seconds. The information age of vacuum exposure began, properly, with LeBlanc and Dobrovolsky and Patsayev and Volkov and Kittinger, and all the animal research that runs beneath them like an aquifer. Decades of chamber work. Decades of altitude testing, primate studies, decompression research, the slow accumulation of data about what the body does when the pressure goes away. Some of that research is deeply uncomfortable reading. The animal studies from the 1960s, the ones that established what full vacuum exposure does to physiology, past the survivable window, used chimpanzees, dogs, and other large primates in decompression chambers at facilities including the Aeromedical Research Laboratory at Holloman Air Force Base in New Mexico. And the methods were not gentle. The data came from animals that did not survive. The safety margins that governed every subsequent human spaceflight program, the margins that kept every astronaut, whoever put on a suit in an airlock, alive, were written partly in the deaths of animals in altitude chambers in the 1960s. This is the cost the field never fully accounts. The human cost has names. Ward, who named the mechanism and never saw it matter. LeBlanc, who felt the mechanism firsthand and survived with a sore ear and a story nobody widely told. The 3 cosmonauts, who died because a valve opened 40 seconds too early, and 40 seconds was not enough time for any of them to close it. The cost beneath the cost, the animal research that provided the data that kept the humans alive, or at least gave the humans the best possible chance. The field absorbed all of this and produced a set of numbers. A set of windows and thresholds and protocols. The 90-second survivability window, the finding that rapid repressurization within roughly 90 seconds of full vacuum exposure gives a meaningful chance of survival and recovery. the 12 to 15 second window of useful consciousness, the 47 millimeters of mercury threshold below which embolism begins, the 87 seconds it took to repressurize Chamber B in Houston because R.L. Clay moved fast. These numbers are not decorations. They are the skeleton of every EVA protocol ever written, the foundation of every emergency procedure in the airlock of the International Space Station. The reason that when an astronaut goes outside the station today, someone on the ground has a script for what to do if the suit fails. The script exists because people needed to know what actually happens, not what the movies showed. Not what a reasonable extrapolation of physics suggested before the data existed. What actually happens, in the body, in sequence, when the pressure goes. The saliva goes first. And then we need to talk about what deep space adds to this sequence. Not the vacuum is the same. What deep space adds is everything else. The radiation picture in deep space is not an abstraction. It is a specific, measurable, physiological threat that NASA has spent decades trying to understand and has not yet solved. The problem is that galactic cosmic rays the high-energy particles that originate outside the solar system, the ones that stream through everything, the ones that the Apollo astronauts saw as light behind closed eyelids, are not stopped by matter the way lower-energy radiation is stopped. They are not stopped by a foot of aluminum hull. They are not stopped by water. They slow down and they lose energy, but they do not stop, and the slowing down creates secondary particles. And the secondary particles create tertiary interactions, and the cascade of ionizing events through biological tissue is not something the body was built to manage. In the 1 second the title is examining, the radiation dose is not acute. 1 second of galactic cosmic ray exposure in deep space is not immediately dangerous in the way that the vacuum mechanics are immediately dangerous, but it is real, it is measurable. In that first second, high-energy particles are passing through the body. Some of them are passing through cell nuclei. Some of them are ionizing DNA. Some of them are depositing energy in neural tissue. The body does not feel this. There is no sensation. There is no warning. The effect is statistical and cumulative, operating on a timescale of months and years. And in the context of a 1 second exposure, it is essentially noise. But it is happening. In the first second, in deep space, the body is already being threaded by galactic radiation, in a way it is never threaded in low Earth orbit. In a way it is never threaded anywhere inside the heliosphere with anything like the same intensity. This matters for the larger question the title is asking, because the title is not really asking about 1 second in isolation. The title is asking what happens to the body in deep space. And the 1 second is the entry point, the most immediate, most visceral, most specific answer, and from inside that second you can see the longer answer opening out. 1 second, the saliva, the lungs, the embolism beginning at the moisture surfaces, the consciousness starting its countdown. 30 seconds, the subcutaneous swelling accelerating, the vapor lock in the venous circulation worsening, the cardiac output falling measurably, the brain running on reserve. 90 seconds, the outer edge of the survivability window. 2 minutes, cardiac contractility still present but output severely compromised. 5 to 7 minutes, the heart loses its battle. Beyond that, the body is no longer a person. It is a body. It continues to change, slowly, in ways that depend on where in deep space it is and what the local radiation environment is doing. It does not freeze quickly. It radiates heat slowly. The radiation continues to pass through it, ionizing tissue that is no longer ionization sensitive in any consequential biological sense. The temperature drops toward background over the course of days. The molecules that were once a person continue to be the molecules that were once a person, subject now only to physics, no longer subject to the biology that made them briefly and improbably organized into a system capable of feeling its saliva boil. There is a man named Jeffrey Landis, a NASA scientist and science fiction writer, a person who has thought about this with more rigor than almost anyone who wrote a paper about survivability at very high altitude, a paper he called Embolism at 1 million feet. And in that paper he walked through the pathophysiology, with the particular clarity of someone who has both the scientific training and the narrative instinct to understand what the data means for a person rather than just for a system. He noted something that stays with you after you read it, that the expectation of non-survivability that dominated the field through the 1960s was based largely on animal research conducted under conditions that were not perfectly controlled, and that the human case is LeBlanc, Kittinger's hand, the industrial chamber incident in 1982 where a man was decompressed over 3 minutes to above 74,000 feet and held there for another minute and survived with intensive medical care, and at 1 year follow-up showed neurological performance superior to. Pre-accident testing suggested that the window was wider than the animal, research indicated. Not wide enough to be comfortable, not wide enough to relax about, but wider than the early data suggested. The industrial chamber incident deserves more than a sentence. In 1982, a technician was decompressed over 3 minutes to an altitude equivalent greater than 74,000 feet well above Armstrong's line, and held at that altitude for an additional 60 seconds. A manager had to break a glass ionization gauge at the top of the chamber to allow air to leak in because the cycle had stopped mid-process. By the time the chamber was opened, the victim had been above the survivability threshold for 1 to 3 minutes. He was cyanotic. He was frothing at the lips. He was bleeding from his lungs. He had grade 4 barotrauma of both eardrums, the worst possible rating on the barotrauma scale, the rating that means the tympanic membrane has ruptured. He was given intravenous medication and recompressed to 6 atmospheres using a specialized gas mixture 5.5 hours after exposure. By 24 hours after exposure, he was awake and alert. By day 5, he was extubated, removed from the breathing machine. At 1 year follow-up, his neurological performance was superior to his pre-accident baseline. Superior, his brain, which had been in the process of starving, and whose blood had been forming bubbles and whose vessels had been under the kind of pressure differential that kills, came back not just to normal, but to better than normal. Nobody fully understands why. The hypothermia that develops during vacuum exposure, the evaporative cooling from the moisture surfaces, the surface temperature dropping may be part of it. Hypothermia has a complicated relationship with oxygen deprivation. In controlled medical settings, induced hypothermia is used to protect the brain during cardiac surgery, precisely because lower temperatures reduce the brain's oxygen demand and slow the cascade of cellular death. The vacuum exposure creates a kind of incidental, uncontrolled, dangerous hypothermia, and that hypothermia may, in some cases, be buying time. The cold that is killing you may be slowing down the rate at which it is killing you. This is not a clean finding. It is not a recommendation. It is a piece of the picture that does not resolve neatly into a lesson or a protocol. It just sits there in the data, uncomfortable and specific. The 1982 case has a published case report. It was written by G.L. Colasari and E.P. Kindwall and published in Aviation, Space and Environmental Medicine in December of that year, Volume 53, Number 12. It runs 4 pages. The patient is not identified by name in the published report. He is a data point. As all patients in case reports become data points, their personhood preserved only in the attending physician's notes and in their own memory of what it was like to have been above the Armstrong line and come back from it. He came back. LeBlanc came back. Kittinger's hand came back. The Soyuz 11 cosmonauts did not come back. And the difference between the cases that survived and the cases that did not is not the physics is the same in every case. It is the window, how fast the pressure returned, whether the right person was in the room, whether the pump was reversed before the window closed. L. Clay was in the room. He reversed the pump. That is the whole of it. Now we are deep enough into the sequence that we can ask the question the title is actually asking, which is not a physics question. The physics question has been answered. The saliva, the lungs, the embolism, the vapor lock, the 15-second countdown, the cardiac cascade, the survivability window, the slow radiation threading through the tissue, the body that does not explode and does not freeze and does not cooperate with the story we were told. That is the physics answer. The question the title is actually asking is about what it means that this is the sequence, that the body responds this way, that the window exists, that the window is exactly as wide as it is and no wider. Think about the window. 90 seconds is not random. It is not arbitrary. It is not a number someone chose. It emerged from the data from the animal research and the human cases and the aerospace medicine literature that accumulated over decades as the approximate duration after which the probability of meaningful survival drops below any reasonable threshold. Below 90 seconds, the right intervention at the right speed can bring you back. Above 90 seconds, the cascade has progressed far enough that even perfect intervention may not be enough. The line is not sharp. There is no moment at which the switch flips from survivable to unsurvivable. It is a gradient, as most things in biology are gradients, but 90 seconds is the middle of the gradient, the place where the odds cross from better than chance to worse than chance. 87 seconds. R. L. Clay managed 87 seconds. Jim LeBlanc was 3 seconds inside the window. 3 seconds. The entire architecture of human spaceflight, the entire accumulated knowledge of aerospace medicine from Harry Armstrong's altitude chambers to Julian Ward's 1956 paper, to the Soyuz 11 investigation to the IS emergency protocols, all of it converges on a 3-second margin in a chamber in Houston in December of 1966. A margin that existed because a technician whose name almost did not survive the telling of the story moved fast. This is not a lesson about heroism. It is a lesson about margins. Every safety system, every emergency protocol, every redundant seal and backup valve and pressurized suit layer, all of it is a way of widening the margin, of turning 3 seconds into 10 seconds, into 30 seconds, into enough. The history of human space travel, viewed through the lens of vacuum exposure physiology, is a history of margin negotiation, of figuring out exactly how wide the window is and then engineering everything possible to keep the window open long enough for someone to reverse the pump. The pump, in this metaphor, is whatever saves you. It is the repressurization system. It is the emergency re-entry capability. It is the rescue sphere, the personal rescue sphere that looks like a large fabric ball, 34 inches in diameter, zipped from the inside, with its own oxygen supply and a small window and a telephone, the last refuge when the suit fails and the station fails and everything else has failed. You climb inside. You zip yourself in. You wait. Someone carries you to safety through open space in a ball. It sounds absurd. It is absurd. It is also the final backup that engineers built because they understood what the window was and how quickly it closed, and what it meant to be 3 seconds on the right side of it versus 3 seconds on the wrong side. No astronaut has ever used the personal rescue sphere operationally. No astronaut has ever needed to be carried through space in a ball. But the ball exists, and it exists because the window is real and the people who designed it understood the window the way you can only understand it if you have looked at the data at LeBlanc in the chamber, at Kittinger's swelling hand, at the Soyuz 11 autopsies, at the case report from 1982, at the animal studies from Holloman and the altitude chambers at Wright Field, and the decades of work that accumulated into a specific number, 90 seconds. The window that makes the difference between going home with a sore ear and becoming a name on an award that most people who study this subject have never heard of. Harry Armstrong. The line is named for him. He founded in the 30s and he lived until 1983, long enough to see everything that his discovery made possible. Long enough to see the space program he helped build in its medical foundations put men on the moon and bring them back. Long enough to see the Soyuz 11 tragedy and the Skylab missions and the early shuttle flights. He died on February 5th, 1983. He was 83 years old. He had been a major general. He had been enshrined in the National Aviation Hall of Fame. He had, at some point in the 1930s, while running experiments in altitude chambers, found the ceiling that no amount of oxygen could push past. The ceiling that was not about breathing, but about physics. The ceiling that was not a ceiling so much as a line where the rules changed. Julian Ward. The word is named for him. He coined it at 35 years old, presented it at a symposium on January 19th and 20th of 1956 at the School of Aviation Medicine, published it in October of the same year, and then continued his work on weightlessness and life support systems, continued his research on the physiology of subgravity, continued being the kind of person who fills in the foundational blocks of a field that other people build on, until an L-20 aircraft crashed near Hahn Air Base in Germany on August 13, 1962, and he was gone. The Aerospace Medical Association named an award for him. Outstanding Achievement in Aerospace Medicine Residency Training. The citation mentions his foundational contributions. Most people who have read the word embolism in a technical paper or an aerospace medicine textbook have encountered his conceptual work without encountering his name. His name is in the etymology: to bubble up, to boil out. Every time someone uses the word, Julian Ward is in it. Invisible, Jim LeBlanc. Nobody named anything for him. He went on to be a division chief at NASA, a career of quiet technical competence, the kind of career that the space program runs on at every level beneath the astronaut corps. His name appears in a Guinness World Record, highest equivalent altitude exposure survived. December 14th, 1966. The record still stands. Nobody has been accidentally exposed to nearer vacuum conditions and survived. He is the record holder in a category that nobody aspires to hold. He remembers the fizzing on his tongue. That memory specific, irreplaceable, belonging to one person on one afternoon in one chamber in Houston, is the ground truth of everything this script has been reporting. All of the physiology, all of the research, all of the safety systems and emergency protocols and 90-second windows and backup spheres, all of it, is an attempt to systematize the thing that Jim LeBlanc felt, without instruments, without preparation, without the benefit of knowing in advance what was happening to him. He felt the saliva go. He felt the first event in the sequence. And then he felt nothing. And then the pump reversed. And then he felt something again. And then he went home. The universe almost let him live. It did let him live. 3 seconds inside the margin, because R.L. Clay was in the room and moved fast. 3 seconds that are now, 60 years later, still the sharpest data point we have about what it actually feels like to be a human body at the edge of vacuum. Not a model, not an extrapolation, not an animal study with all its uncomfortable methodology and its findings that require extrapolation to the human case. A person. His tongue. The fizzing. Everything else, the biochemistry, the vapor pressure equations, the cardiac cascade, the recovery data, the radiation threading through the tissue in deep space, the slow radiative cooling, the window, everything else is context for that moment. The moment when the saliva goes and the body begins its hierarchy of failures in an order nobody predicted, in a sequence that is stranger and more survivable and more demanding of exactly the right response at exactly the right speed than anything the movies imagined. The movies gave you the explosion. The explosion is clean. The explosion ends the question before it becomes uncomfortable. The window makes it uncomfortable, because the window means the question is not whether the body can survive it, is whether the response is fast enough, whether someone is in the room, whether they move before the margin closes, whether R.L. Clay is there. And now think about what it would mean to be not in a chamber in Houston, not 30 seconds from a repressurization pump and a medical team, and an exit through 3 pressurized doors, but in deep space, where the distance to the nearest repressurization is measured not in seconds but in the physics of orbital mechanics and propulsion, and the hard constraints of where human beings have so far managed to put themselves in the universe, where the pump, even if someone is reaching for it, is too far away to make any difference, where the window closes and there is no one on the other side of the glass. That is what deep space adds to the sequence. Not different physics, different geography. The saliva still goes first. The timeline still runs to 12 to 15 seconds. The window still exists. But the window, in deep space, opens into nothing. There is no pump. There is no Clay. There is the sequence, in its specific order, running to its specific end, without the intervention that makes Leblanc's story different from Dobrovolsky's story. Dobrovolsky had 40 seconds. The valve was beneath his seat. The atmosphere was already gone before the choice was fully available. 40 seconds is longer than the useful consciousness window, but shorter than the time it would take to find the valve and close it under the conditions of an explosive decompression, as Leonov's simulator test confirmed. 40 seconds, and the right man's hands on the valve might have been 12 seconds, 15 seconds, the swelling already starting in the fingers, the cognitive function already degrading, the body already doing what bodies do when the pressure goes. We do not know if Patsayev reached the valve. We know he was found near it. We know that the autopsies found the hemorrhaging and the lactic acid and the evidence of a system that had been fighting the cascade and losing. We know that he was a research engineer, the first person to operate scientific equipment in space, a man who had spent 23 days on the first space station in history and was 3 minutes from coming home. We do not know what his last 12 seconds were like. We know what the sequence is. We know what order the body follows. We know that the saliva goes first, and that after the saliva the consciousness has 12 to 15 seconds, and that after the consciousness the heart keeps going for minutes in the dark. We know that the heart keeps going for minutes in the dark. This is the part of the sequence that is hardest to sit with. The brain has gone the consciousness, the sense of self, the experience of being a person rather than a body, and the heart is still there, still doing what hearts do, still cycling through its electrical signal and mechanical contraction, with the stubborn autonomic persistence that evolution built into the cardiac muscle over 400 million years of vertebrate history. The heart was not designed to know when to stop. The heart was designed to keep going. It keeps going against vapor-locked veins. It keeps going against falling arterial pressure. It keeps going until the cascade progresses far enough that even the cardiac muscle cannot maintain its cycle without sufficient oxygen delivery, until the myocardium itself begins to fail, and then, somewhere between 2 and 7 minutes after exposure, it stops. 2 to 7 minutes. The range is wide because the variables are significant. The initial state of the individual, the rate of decompression, the exact nature of the vapor lock, whether any residual circulation was maintained through the period of consciousness, loss, all of these affect where in the range a particular case falls. But the range is real. For 2 to 7 minutes after the saliva goes and the consciousness goes, the heart is in the body, trying. It is trying in a person who is no longer there to know it is trying. This is the weight of the whole sequence. Not the explosion, there is no explosion. Not the instant freeze, there is no instant freeze. The weight is in the quiet continuation. The body, long past the point where it is a person, still running through the motions of being a person, still cycling the cardiac muscle, still maintaining the autonomic reflexes that were never designed to receive a signal to stop. The architecture of biological persistence, the same architecture that keeps a heart beating in a chest that has no other function, running in deep space, with no one watching it, running until the fuel runs out. And then, after the fuel runs out, the slow things begin. The temperature dropping through radiation, 1 degree at a time, over hours and then days. The radiation from deep space continuing to pass through tissue that no longer registers it as damage in any consequential sense. The molecules remaining molecules, organized in the specific patterns that were once a person, subject now only to the long-term chemistry of vacuum and radiation and time. There is no corruption in vacuum, no bacteria, no oxidation. The normal biological processes of decay require the chemicals and microorganisms that vacuum cannot support. The body does not decay. It desiccates.
The moisture that was not already lost in the ebulism of the first seconds sublimes slowly through the skin, and the body becomes something between preserved and frozen, a form of accidental mummification, and then over centuries the radiation and the occasional particle impact begin to break down the molecular structure and the molecules that were once organized into a person with a name and a job title and a memory of the fizzing on their tongue disperse into the medium of interstellar space, which is not empty but is the closest thing to empty that exists in the physical universe. A near-perfect vacuum with a particle density of roughly 1 atom per cubic centimeter, a density so low that by the standards of any environment,
1 atom per cubic centimeter. the medium into which the molecules eventually disperse, the context in which the whole sequence, the saliva, the lungs, the vapor lock, the 15 seconds, the cardiac persistence, the slow cooling takes place. This is what deep space is.
Not the dramatic emptiness of the movies, not the cold death and the exploding bodies, but a medium of extraordinary and precise emptiness in which the human body performs its cascade of failures in a specific order that took decades to understand, that cost at least one life in the understanding, that was named by a man who died before he saw the naming matter, and that was felt personally, specifically, in the fizzing of saliva by a technician in Houston whose name belongs in this story more than any astronaut's name does, because he is the only person who felt the sequence from the inside and came back to say what it was like.
The saliva goes first. Jim LeBlanc felt it. He stumbled backward in Chamber B of Building 32 at the Manned Spacecraft Center in Houston, Texas, on December 14, 1966. The window was 90 seconds wide. R.L. Clay reversed the pump in 87 seconds. LeBlanc woke up as the chamber pressure climbed through 14,000 feet equivalent, and the first thing he was aware of was being alive. And the first specific thing he could report from inside the sequence was the fizzing on his tongue before the darkness came. 3 seconds inside the margin. This is what the universe gave back in exchange for 3 seconds, the specific knowledge of what the first event in the sequence feels like. From the inside, in a person who survived it. Not an instrument reading, not an animal study, not a model or a calculation or an extrapolation from data gathered under conditions that required subsequent correction. A person's account of a specific sensation. At the specific moment the pressure went away. The saliva goes first. It fizzes. It is not painful. Your brain cannot classify it correctly, because nothing in human evolutionary history prepared it for this classification. And then the darkness comes. Everything after the darkness is physics. Everything before it was you. There is a question that the physiology does not answer, and it lives just past the edge of what the data can reach. The question is about the 15 seconds, not what happens during them that has been reported. The vapor lock, the falling arterial pressure, the brain running on its dissolved oxygen reserve. The countdown that the body does not know is a countdown. The question is about the quality of those 15 seconds, whether the person inside them knows what is happening. Whether the cognitive function that remains in the first moments after the pressure drops is sufficient to understand the nature of what is occurring, or whether the hypoxia that arrives simultaneously with the embolism degrades the processing fast enough that the experience is less than understanding, more than nothing a kind of twilight between comprehension and absence that the data cannot reach, because the data comes from people who survived, and from autopsies of people who did not. And neither source has access to what the 15 seconds felt like from the inside. LeBlanc had the saliva, he had the stumbling, he had the darkness. He did not have the intermediate region, the seconds between the sensation and the unconsciousness, because the unconsciousness arrived before he could encode anything between them. His account goes, the fizzing, and then nothing, and then the chamber monitors calling 14,000 feet. There is no middle. The middle is missing from the record. This is not unique to LeBlanc. Every human account of vacuum exposure has the same gap. The sensation, and then the gap, and then the waking up. The gap is the 15 seconds, and the 15 seconds are the part of the story that nobody has ever reported from inside. Not because nobody experienced them, but because the experiencing of them does not survive the transition back to consciousness in a form that can be articulated. The brain, coming back online during repressurization, does not retrieve what the brain was doing during the blackout. The memories are not encoded. The lights went out before the recording stopped. This is a specific kind of not knowing that sits differently from ordinary ignorance. We do not know, for instance, exactly what the temperature of the sun's corona is at every point, but the not knowing there is a matter of insufficient measurement, a problem of instrumentation and access that is in principle solvable. The not knowing about the 15 seconds is different. It is structural. The mechanism that would need to preserve the information is the same mechanism that the 15 seconds are in the process of destroying. You cannot remember what you experienced while your memory-making apparatus was failing, because the failing is exactly the thing that prevented the memory from being made. What this means for the story is that the 15 seconds are the permanent interior of vacuum exposure, the part that stays inside, that does not come out in the case report or the first-person account or the technical paper. Every person who has ever passed through that window and come back has left those seconds behind in the gap between the sensation and the darkness, and they are unretrievable by any method currently available. They happened. They were experienced in whatever degraded, fragmentary, cognitively compromised way that hypoxic half-consciousness constitutes experience. And they are gone. The only people who retained the 15 seconds did not come back. Think about what that means for Patsayev, for Dobrovolsky, for Volkov. The 3 cosmonauts of Soyuz 11 had, by every physiological account, approximately 15 to 20 seconds of degrading consciousness after the valve opened. The data from Dobrovolsky's biomedical sensor shows the cardiac arrest at 40 seconds, which means that for the first 20 to 25 seconds after the valve opened, the heart was still maintaining something resembling normal rhythm. The pressure in the cabin was dropping but had not yet reached the level of full physiological catastrophe, and the brain was functioning well enough to receive sensory input and process it, however imperfectly. Those first 20 seconds existed. They were experienced by 3 people whose names are on craters on the moon, whose photographs were carried to lunar orbit on the Apollo 15 mission, whose state funeral was attended by Tom Stafford as a representative of the United States government, whose deaths changed the design of the spacecraft that every subsequent Soyuz crew has flown in for more than 50 years. What did they know? In those 20 seconds, the valve was beneath Patsayev's seat. The autopsy found him positioned near it. He may have been moving toward it before the hypoxia took his coordination. If he understood what was happening, if the pressure loss was fast enough to feel like something definite, if his aerospace medicine training told him what the sensation meant, then he may have had a window of comprehension before the window of function closed. He may have understood. He may have known that the valve was there, and that the time was not enough, that the geometry of the cabin and the speed of the decompression and the distance between his hands and the valve were a calculation that did not resolve in his favor. Or the hypoxia may have been fast enough that the comprehension never fully formed, that the sensation of pressure loss translated to confusion before it translated to understanding, that the training was submerged before it could be accessed. We do not know. The gap is there as it is always there, in every vacuum exposure case, in every moment when the recording stops before the event is finished. This not knowing is part of what makes the subject difficult to leave. The physiology is answerable. The sequence is documented. The window is measurable. But the inside of the window, the experience of being in the 15 seconds, is permanently inaccessible, held by people who are no longer available to be asked, encoded in the neural tissue that the autopsies examined without being able to read. This is where the story stops being about aerospace medicine and starts being about something that aerospace medicine does not have a word for: the gap between what happened and what was experienced, between the external record of the cascade and the internal record that did not survive the cascade. Every safety protocol in human spaceflight is an attempt to prevent someone from being the person who holds that internal record permanently. The whole architecture, the suits, the windows, the pumps, the 90-second survivability envelope, is an attempt to ensure that the internal record comes out of the gap with the person, that the experiencing is followed by the remembering, that the story of the 15 seconds can eventually be told rather than permanently held. LeBlanc almost held it. 3 seconds closer and he would have held it. 3 seconds in the gap would have been everything, and R.L. Clay would have been a different kind of entry and a different kind of record. And the specific memory of the fizzing on the tongue, the only first-person account of the first event in the sequence, would not exist. 3 seconds. The margin. Again, it keeps returning to the margin, because the margin is what the subject is actually about, once you have worked through all the physiology. The margin is the thing that every researcher in this field was actually studying, whether they named it that way or not. Harry Armstrong was studying the margin when he ran his altitude chamber experiments in the 1930s. He was trying to find where the margin ended, where the physics became absolute and no amount of engineering could extend the window further. Julian Ward was studying the margin when he wrote about embolism. He was trying to understand the mechanism precisely enough that the margin could be quantified and therefore designed against. Every NASA engineer who ever worked on suit pressure integrity was working on the margin. Every protocol for EVA pre-breathe, for suit-up sequence, for airlock operation, every procedure in the 1,000-page EVA operations manual that governs a spacewalk on the International Space Station is the margin, written down, turned into steps. The margin is what the space program actually is, at the physiological level. The margin between what the body can survive and what the environment presents. The margin between the 90-second window and the time it takes to reverse the pump. The margin between Patsayev's hands and the valve beneath his seat. For every mission that has gone without a vacuum fatality, for every EVA that has ended with the astronaut safely back inside, for every launch and re-entry that has gone nominally, the margin held. The engineering was sufficient. The training was sufficient. The luck was sufficient. And calling it luck does not diminish the engineering and the training, it just names the third element that is always present in any system operating at the edge of what the physics will allow. For Soyuz 11, the margin did not hold. The explosive bolts fired together, the valve unseated, and the margin was not 0, the margin was 40 seconds. The time from the valve opening to the cardiac arrest, but 40 seconds, was a margin that the geometry of the capsule and the speed of the pressure drop did not allow to be used. The margin existed in time, but not in space. Not in the distance between hands and valve. Not in the cognitive clarity that the hypoxia was already eroding as the seconds ran. 40 seconds is longer than people think. Until you are trying to find a valve you cannot see beneath your seat, while the atmosphere is screaming out of the capsule, and your hands are starting to behave differently than hands are supposed to behave, and your vision is narrowing at the edges and your training is somewhere in your head, but the pathways to it are becoming unreliable. 40 seconds is not enough. The margin was there and the margin was insufficient, and the distinction between those two things is where the weight of the story lives. Now there is something else in the deep space version of this story that has not been fully accounted for, and it concerns what happens to the sequence when you remove not just the repressurization pump, but every assumption that the vacuum exposure research was built on. Every human case in the literature, LeBlanc, Kittinger, the 1982 industrial chamber incident, the Soyuz 11 tragedy occurred in low Earth orbit or in a ground-based chamber. Every animal study occurred in the same context. The research base for vacuum exposure physiology was built in environments where the gravity was approximately 1 g, or approximately 0 but never negative, where the nearest star was at the same distance it has always been, where the radiation environment was partially shielded by planetary magnetospheres and the solar wind, where the temperatures of nearby surfaces ranged from extreme but finite values rather than from the near absolute zero background of interstellar space. Deep space is a different physical environment in ways that the vacuum exposure research does not fully address. Not different in its vacuum, the vacuum in deep space is not more or less vacuum than the vacuum in Chamber B in Houston. Vacuum is not a matter of degree once you are past the Armstrong line. But the context surrounding the vacuum changes, and some of those contextual changes have physiological implications. The gravitational environment in deep space is not 0 g the way low Earth orbit is 0 g. In low Earth orbit, the spacecraft and everything in it is in free fall, orbiting at sufficient velocity that the fall continually misses the Earth, and the experience of weightlessness is the experience of continuous free fall. In deep space and interstellar space, genuinely beyond the influence of any nearby star, the gravitational field is not 0, but is so weak as to be negligible by any biological standard. The practical difference between 0 g in Earth orbit and the gravitational conditions of interstellar space is not significant for the purposes of vacuum exposure physiology. The body floats in both. The fluid shifts that occur in microgravity, the familiar puffiness of astronaut faces, the fluid moving headward as the normal gravitational gradient that keeps it lower body biased, disappears. These would occur in both environments. They are not the dominant physiological event in vacuum exposure, but they are part of the context. The radiation context in deep space is substantially different, and this has been partially addressed but deserves more precision. The galactic cosmic ray environment beyond the heliosphere is not simply more intense than in Earth orbit, it is different in character. Inside the heliosphere, the solar wind modulates the incoming cosmic ray flux, pushing back against the particles streaming in from the galaxy. The modulation is energy dependent and variable with the solar cycle, but it is real and it is significant. Beyond the heliopause, this modulation disappears. Voyager 1's instruments recorded the change clearly when it crossed the boundary in 2012. The intensity of low-energy cosmic rays increased sharply, the signature of particles that the solar wind had been keeping out. Higher-energy cosmic rays were present throughout the heliosphere, but the spectrum changes in interstellar space in ways that matter for biological dose assessment. For a body exposed in deep space, the radiation dose rate is higher than anywhere in the inner solar system, and is dominated by high-energy heavy ions, the component of galactic cosmic rays that is most biologically damaging per unit of physical dose because of its high linear energy transfer, the density of ionization it deposits along its path through tissue. These particles cannot be shielded effectively by any reasonable amount of material. They pass through. They ionize along their track. They create secondary particles that ionize further. The DINA damage from high-LET radiation is qualitatively different from the DINA damage from low-LET radiation like X-rays. The damage is more complex, more likely to involve double-strand breaks in close proximity, more difficult for the cell's repair mechanisms to address correctly. The cancer risk from galactic cosmic ray exposure is not just greater in magnitude than from X-ray-like radiation. It is different in nature. For a vacuum exposure event in deep space, the radiation dose accumulated in the first second is still not the acute hazard. The first second of cosmic ray exposure does not measurably alter the physiological cascade. The vacuum mechanics dominate in the first second, in the first 90 seconds, in the first several minutes. The radiation operates on a longer time scale. But there is an interesting intersection point, the point where, if somehow the vacuum exposure were survived by some future technology, some intervention mechanism not yet developed, some means of repressurization in deep space that does not currently exist, the radiation exposure accumulated during the unconsciousness and the cardiac continuation and the slow recovery would represent a dose that is meaningfully different from the dose accumulated during an equivalent period in low Earth orbit. The deep space survivor, the hypothetical person who somehow made it through the vacuum exposure and was repressurized in deep space, would carry a different radiation burden than the chamber survivor or the low Earth orbit survivor. This hypothetical person does not exist. But the thinking through of their situation clarifies what deep space adds to the sequence. Not a different first second, but a different context for every second after the first. And a different context for the recovery if recovery were possible. And a different long-term physiological picture for any survival scenario that the physics can be made to support. There is also the question of what happens to the saliva in the specific thermal environment of deep space. The boiling of body fluids at Armstrong's line is driven by pressure, not heat. This has been established. But the thermal environment in which the ebulism occurs matters for the energetics of the process. When a liquid transitions to vapor, it absorbs the latent heat of vaporization from its surroundings. At sea level, when you sweat, the evaporation of sweat from your skin cools the skin because the water molecules escaping into vapor carry thermal energy with them. The same process operates in vacuum, but at a larger scale and with no medium to carry the vapor away. The saliva and the corneal moisture and the airway fluid flashing to vapor in vacuum take thermal energy from the surfaces they were coating, and those surfaces cool. How much cooling depends on the total volume of moisture involved and the thermal properties of the tissue. In deep space, The thermal environment surrounding the body is the cosmic microwave background at 2.7 Kelvin and whatever radiation the body can emit into the vacuum. There is no warm spacecraft interior, no chamber wall at ambient temperature, no air being circulated at room temperature. The body is in the coldest macroscopic environment that exists. The evaporative cooling from the embolism is occurring into an environment that will provide no thermal return. The surface cooling is more extreme than in a ground chamber. Whether this makes a meaningful difference to the physiological cascade in the first 15 seconds is not clearly established in the literature, because all of the experiments were conducted in chambers at ambient temperature, not in thermal environments approaching absolute zero. The theoretical expectation is that the surface cooling is faster and more extensive in the deep space thermal environment, which may accelerate the freezing of the corneal moisture layers and may affect the rate of subcutaneous water vapor formation. Whether it changes the 15-second timeline meaningfully is unclear. What is clear is that after the consciousness goes and the cardiac cascade continues and eventually concludes, the cooling of the body in the deep space environment proceeds by radiation alone and proceeds toward a background temperature of 2.7 Kelvin rather than toward the ambient temperature of a chamber or a spacecraft interior. The eventual equilibrium is colder by more than 260 degrees Celsius than any ground-based experimental analog. The body does not reach this equilibrium quickly. The radiative cooling is slow, as established, but it reaches it eventually, and the structure that results is preserved at a temperature that no decay process can operate on, in a vacuum that no oxidation can reach, in a radiation environment that slowly works on the molecular bonds over timescales that make the age of the universe seem preliminary. The molecules persist, changed by radiation and time, but persistent. The specific arrangement of atoms that was once a person, that once felt the fizzing of boiling saliva and had a job title and a name, persists in a form that is no longer any of those things, but is not yet returned to the undifferentiated medium of interstellar space. Interstellar space is not nothing, and this matters. The popular conception of deep space as empty is technically inaccurate in a way that has no practical consequence for the physiological cascade, but has a strange resonance when you think about what the body disperses into. Interstellar space contains, on average, roughly 1 atom per cubic centimeter. In the denser regions of the interstellar medium, the molecular clouds, the regions of active star formation, the density is higher. In the voids between galaxy filaments, it is lower, but the average is 1 atom per cubic centimeter. Compare this to the air you are currently breathing, which contains approximately 27 million trillion atoms per cubic centimeter. Interstellar space is not nothing. It is just very, very close to nothing. It is the closest approximation to absolute emptiness that the physical universe provides, and the human body in interstellar space is the densest object for an immense distance in every direction. This is a strange thing to hold in mind. A human body which is itself mostly empty space at the atomic level, electrons in probability clouds around nuclei, separated by distances that dwarf their own diameters, is an extraordinarily dense object relative to the medium around it in interstellar space. The body is a local anomaly, a concentration of matter in a region of near total diffusion. The molecules that compose it are in a configuration of almost unimaginable improbability, relative to the equilibrium state of the surrounding medium, and the trajectory of those molecules over time is toward that equilibrium, toward the diffusion that entropy requires and that nothing in the vacuum of deep space is capable of preventing. But it takes a long time, a very long time. Long enough that the distinction between preserved and dispersed is not the work of seconds or years, but of something closer to geological time, and in the specific thermal and radiation environment of deep space, longer even than that. The body holds together in deep space for a very long time after the sequence ends. This is not a comforting thought exactly, and it is not meant to be. It is a fact about the persistence of matter in an environment that we tend to think of as annihilating. Deep space does not annihilate, it preserves. It changes slowly through radiation damage to molecular bonds and through the occasional impact of an interstellar grain, but it does not dissolve. The body in deep space is not consumed. It is held at 2.7 Kelvin in a near-perfect vacuum, being threaded by cosmic rays that ionize a bond here and a bond there on timescales that stretch past anything biology has language for. The sequence in this sense does not end at the cardiac conclusion. The sequence ends when the last molecular bond specific to the original arrangement breaks, when the last protein loses its folded form, when the last strand of DNA loses its base pair sequence to radiation-induced damage, and becomes, finally, just a chain of small molecules floating in interstellar space, indistinguishable from any other small molecules in the medium. This ending is so far in the future that it is not practically meaningful to any human purpose, but it is the actual end of the sequence, the full accounting of what deep space does to the body that entered it. Everything before the cardiac conclusion is physiology, everything after it is chemistry, then eventually, physics again. Now there is something that the aerospace medicine literature acknowledges only at the edges, something that is not strictly a physiological finding, but that emerges from the physiological picture in a way that cannot be avoided if the reporting is honest. The 90-second window is an engineering parameter. It is the number that tells designers how fast the repressurization system needs to work. It is the number that determines the inflation time of the personal rescue sphere, the capacity of the emergency oxygen supply, the response time required of the chamber operators and the airlock controllers and the ground team. It is a design target, but it is also a description of what the body will accept. This is a strange way to think about a physiological limit, but it is accurate. The body will accept 90 seconds of vacuum exposure, if the intervention is correct, and return to function. The body will not accept 2 minutes in the same way. The body will accept 3 seconds of margin between the window closing and the pump reversing. The body will not accept 0 seconds of margin. These are not preferences, they are parameters. The body does not have an opinion about them. But they are, in their specific values, a description of what the biological system that is a human being can absorb and return from, and those specific values were not designed. They emerged from the chemistry of the blood and the physics of vapor pressure, and the electrical properties of cardiac muscle, and the oxygen storage capacity of cerebral tissue, and 400 million years of vertebrate biology that never anticipated this particular challenge but produced, incidentally, a system robust enough to survive the first 90 seconds of it, if the engineering is fast enough. The body did not know it had a 90-second window until we forced the data out of it. The data came from animals that did not survive, and from humans who almost did not survive, and from 3 humans who did not survive, and from 1 man who survived with a sore ear and a memory of fizzing. And all of that constitutes the knowledge base for a window that the body has been carrying since before it was a body in the sense we mean when we say human body, since before the species existed, since before the genus existed, since before anything with a circulatory system had occasion to think about what space would do to it. The window predates the concept of space. It predates the concept of vacuum. It predates the concept of pressure. The cardiac muscle that keeps beating past the loss of consciousness, the cerebral oxygen reserve that buys 15 seconds of function, the skin that holds against the pressure differential. The corneal surface that takes the evaporative cooling and survives at all of this was evolution solving problems that had nothing to do with vacuum and producing. As a side effect, a system with specific tolerances that would one day be studied in altitude chambers in the 1930s and 1940s, and measured in a chamber in Houston in December of 1966, and turned into a number that engineers could design against. 90 seconds. The number that connects Harry Armstrong's altitude chambers at Wright Field in the 1930s to the personal rescue sphere floating in a Soyuz module. The number that R.L. Clay beat by 3 seconds. The number that the Soyuz 11 crew did not have available to them, because the margin in their case was not time, but geometry, and geometry is not something you engineer around with a faster pump. There is one more thing that the reporting found. and it lives in the space between the physiology and the story of how the physiology was learned. The learning was not clean. The history of vacuum exposure research is not a clean progression from ignorance to knowledge, from wrong assumption to correct measurement. It is a history of uncomfortable methods and buried data and findings that took decades to reach the public literature, and names that almost did not survive the telling. The animal research, the chimpanzees and dogs and large primates in the decompression chambers at Holloman and at Wright Field and at the other facilities that participated in the altitude research of the 1950s and 60s was not designed to produce publishable findings about the welfare of the animals. It was designed to produce data about survivability thresholds that could be used to establish safety margins for human spaceflight. The animals were the margin research. They were the data that allowed the human window to be quantified before any human crossed it accidentally. This is not an argument against the research. The human spaceflight program that the research supported has not killed a crew member through vacuum exposure. Every EVA that has ever been conducted by a human being has been conducted against a safety architecture that includes, at its foundation, data from animals that did not survive the testing. The argument against the research and the argument for it are both real arguments, and they do not resolve cleanly, and the aerospace medicine literature does not dwell on them. Because the aerospace medicine literature is focused on the engineering and the physiology, rather than on the ethics of how the data was obtained. But the weight is there. The weight is in the foundation. Julian Ward named the mechanism and died before he saw it matter, and the weight is in that. R.L. Clay reversed the pump and saved a life, and had his name almost erased from the record, and the weight is in that. The Soyuz 11 cosmonauts died because explosive bolts fired simultaneously instead of sequentially, because a manufacturing tolerance was not tight enough, because a design review did not catch a failure mode that was physically present in the system, and the weight is in the specificity of that failure, the way it came from something so mechanical, so unglamorous, so distant from the heroism the mission represented. The space program looks, from the outside, like ambition and courage, and the organized will of civilization reaching beyond its atmosphere. From the inside of the physiology, it looks like a set of margins held open by specific people on specific afternoons, who moved fast or who did not move fast enough, and by the residue of research conducted in conditions that the field does not revisit publicly, and by the legacy of a man who coined a word and died at 35, and whose name has been carried forward in the Latin without most of the people who use it knowing whose name they are carrying. This is not a criticism of the space program. It is a description of what it actually is at the level where the body meets the environment. The body has a 90-second window, and the space program is the civilization scale effort to make sure the window is never the thing that fails. The effort is genuine. The cost is real. The names that are carried without being known are many. The margins are everything. And through all of it, running underneath the research and the protocols and the engineering and the tragedy and the 3-second margins, there is the fizzing. The specific sensation on the tongue in the first moment of vacuum exposure, the sensation that Jim LeBlanc described, and that every subsequent account has had to work around because there is no laboratory analog for it and no way to produce it experimentally without producing the entire vacuum exposure along with it. The sensation that is not pain and is not cold and is not any of the dramatic things the movies offered as substitutes. The sensation of moisture transitioning state on a surface that has never been asked to experience this transition before, in a body that has no evolved response to it, in a moment that the consciousness will not survive long enough to fully process. The last sensation before the window. Every measurement that exists about vacuum exposure, every millimeter of mercury and every second of useful consciousness, and every case report, and every animal study and every safety margin and every protocol in, every EVA operations manual is an attempt to ensure that the fizzing is not. The last thing, that after the fizzing there is a pump, a person, a margin, enough time for the sequence to be interrupted and reversed, that the window opens and the person comes back through it, LeBlanc came back through it. His saliva returned to liquid on his tongue. His consciousness returned to function as the chamber pressure climbed. He walked out of Building 32 in Houston on December 14, 1966. And he went home. And somewhere in the record of aerospace medicine, his experience lives as a data point and a case history, and a Guinness World Record, and the clearest first-person account of the first event, in a sequence that the field has spent 80 years trying to understand well enough to prevent. He felt the thing that the sequence begins with. He reported it accurately, and the reporting has been held in the literature ever since, specific and irreplaceable, the ground truth of what the body encounters in the first second of vacuum exposure, available to any engineer or physician or researcher who needs to know what they are designing against. Not an abstraction, not a model, not an extrapolation from animals or a theoretical calculation from vapor pressure equations. A memory. A man's specific memory of a specific afternoon when the physics of pressure and the chemistry of body fluids and the engineering of a disconnected hose converged on a single moment in a chamber in Texas. And the moment was survived, and the memory survived it, and the memory says, the saliva goes first, it fizzes. And then the darkness comes, and the heart keeps beating, and somewhere on the other side of the darkness is either a pump that reversed in time, or the slow machinery of deep space, continuing its work on a body that no longer knows it is there. The window is everything. Everything else is what happens when the window closes.